Welcome to tonight's program on molecular machining. My name is Jimmy Gia, and I am the chair of the MIT Enterprise Forum Northwest. We are a part of a global organization of 25, 26 chapters or so, not just in the US, but also in places like Pakistan and the Middle East, and Thailand, actually, which is one of our newest chapters. We are affiliated with the Massachusetts Institute of Technology through the MIT Technology Review, and we're here to inform, connect, and coach technology entrepreneurs, enabling them to rapidly transform ideas into impactful companies. And how many of you here are attending your first event of the chapter? Well, welcome, and I hope to see you at one of our future programs later on this year. Our next one is on connecting cities, looking at smart transportation, and then our season finale is on 3D bioprinting. And both of those should be really, really good programs. None of these programs would be possible without our dedicated volunteers. So a thank you to Mark Anderson, Tim Mack, Jamie Mendez, Chris Puri, Chris Samoji, Nicole and Max Coddington, Shirley Lundy, Paul Meehan, Vicki Owens, and Adam Schuster. Would you please give them a round of applause? And if you are interested in helping us put on one of these programs, just find one of us with these flappy things, and we'd be happy to get you involved. These programs are also made possible by our sponsors, and this year our premier sponsor is T-Mobile, lead sponsor is Artifact, and our STEM sponsor that helps us subsidize student tickets is also T-Mobile. Freelock Computing, MIT Club of Puget Sound Video are our in-kind sponsors, and Stoke Lawrence is our program captain. Without further ado, our moderator tonight is Dr. Michael Cabase from the University of Washington. He is the Associate Director of the Washington Nanofabrication Facility, where he runs the number of their clean rooms, and he works with the students and faculty in their state-of-the-art tools to further their expertise and knowledge to stimulate economic growth. So Michael, welcome to the stage.
Thank you very much. Good evening. Appreciate you coming out and braving the rain. You know, I was a little apprehensive when I was first asked to give a talk on molecular manufacturing. They said, oh, it's a nanotechnology talk. So I said, okay. We're going to be splitting this evening between some traditional nanotechnology, inorganic systems. So two of our speakers will be covering that, myself included, and then we'll have some more that are focused on more of the molecular end of things and some of the biological engineering. So when they asked me to present Star Trek Replicators, as the synopsis said on the website, it's a little hard-pressed to find something. The closest I could find is a 3D printer for pasta, and so that is as close to replication that I could find in state-of-the-art technology. So if you're into designer pasta, we've got a solution for you. If you want Earl Grey on the spot that materializes, we've got quite a bit of research to be doing. However, I believe in May, there'll be a forum on 3D bioprinting where we work with some of the faculty at the university where we're exploring 3D printing of organs, which I find far more fascinating than printing or replicating a cup of Earl Grey. So please consider coming in May to that forum to learn a little bit more about advanced replication. We've also had a promise of some nanites or microbots. And in this case, the closest I could find is swarming bacteria. And these swarming bacteria right now are moving these photolithographic defined polymers. And this is work coming out of the University of Pennsylvania, where they're able to program or control or provide stimuli to these swarming bacteria to help motorize these nano devices. So that's about as close as we get to nanites today. But it's a good theme for this evening because what I'm going to be really focusing on is the fact that we're seeing an integration of bio devices, bio interfaces, and traditional electronics. And I really think that's a theme that will continue to grow as time evolves. So one of the challenges I have as a nanotechnology director is a lot of people will ask, what do you do? And they come up to me and they're like, so what do you do? And I say, well, I'm director of a nanofabrication lab, and I usually get a blank stare if they're not in my field. And the answer is really complex because nanotechnology is a wide range of different technologies. Nanofabrication, of course, is my background, so traditional IC manufacturing or integrated circuits, advanced packaging, a lot of material science that goes into that. My talk will be mainly focused on that, but we also delve into molecular biology, so understanding cell functions, components of cells, how they integrate and work. So we'll have some talks that will be covering that. Surface science really is the analysis of what happens between two phases, whether it's physical or chemical. So monitoring atomic impurities on the surface, looking at AFMs, so atomic force microscopy, looking at surface roughness at the atomic scale. That's that type of research. Semiconductor physics, things like traditional control of conductivity, photonics, electrophotonic interactions, quantum physics. So these are areas of study that are in the state of the art of the work that we do. And then molecular engineering, where we're actually designing designer molecules to improve materials, improve surface science, to mimic biology. So all these are really nanoscale, so something between 1 nanometer or sub-nanometer up to 100 nanometers really is the definition of nanotechnology, and either observing that material or manipulating it for some purpose. So that's what we're going to be focusing on. We'll be bridging between those different technologies tonight. So I'm going to step back and kind of look at what is the technical revolution that's next. Historically, in the last few decades, we've had a major revolution per decade. So in the 80s, we had a PC revolution. The mainframes got onto people's desktops, people embraced it, and it fundamentally changed the way we work. The internet revolution, of course, in the 1990s, we started connecting at a much higher level, and it revolutionized and changed the way people interact, the way communications and information is assimilated and also communicated. And then, of course, the mobile revolution in the 2000s, where we now ended up with these devices where we have that connectivity. Now, none of them actually replaced each other, right? So these technical revolutions, if you look at what a technological revolution is, the formal definition says that it's a new set of technology that replaces a former set of technology. And I have to say with the PC, with this information technology revolutions, they really build on each other. And so they're more evolutionary versus revolutionary, but they do fundamentally change how we work. So the question is, for this decade, really, what is the thing? What are we going to see? Is it the IoT buzz? You know, the fact that my coffee machine knows when I'm out of coffee, does it matter? Robotics and drones, and I'll tell you, I'm really excited about self-driving cars after sitting through traffic yesterday. I'm hoping that's something that will revolutionize how we live. Is it AI? Is it the fact that my cell phone is starting to anticipate my needs? Or is it a confluence of that, where IoT merges with AI, and so I have a fully connected life where I'm actually being assisted in ways that I haven't anticipated yet? Or is it virtual and augmented reality? Are these designed computer-human interfaces at a higher level really going to fundamentally change the way we work, entertain ourselves, interact with each other? Or even more drastically, synthetic biology. And so I'm hoping some of our speakers will really talk about designer molecules, designer cells, changing fundamentally how we work. And I think that technology is far more powerful and disruptive than the evolutionary IT technology. And where they converge is this nanobio interface, where we have electronics and the human body actually interfacing and working together. We have integration, and I'll touch very lightly on ways that we're looking at mimicking biological systems and also integrating biological systems into our electronics. All right, so is evolutionary technology bad? No, it's essential to enable these revolutions. So the example I have here on the right is, you know, an old Google data center that was capable of 1 gigabit per second, and we've actually evolved the photonics technology such that we can get a single channel and get 50 gigabits per second. on a single line, okay? So those evolutions have enabled the fact that we can transmit much more data over, and it's enabled those technologies to continue to grow and build off each other. Of course, when you introduce a technological revolution, it, as a positive, fundamentally changes our way of living and working, but it also has unintended consequences. So the picture on the right is a pretty popular image that shows one of the Pope's inaugurations in '05, and then after the mobile revolution in 2013, you can see that the humans engaged in there have fundamentally changed their behavior, right? Now we're recording this information and capturing it on our mobile devices, which is a powerful technology, but it also has an unintended consequence. And the unintended consequence is there's a study that shows that people that capture those moments on their mobile devices are focused on the capture and not focused on the event. So they don't have a memory that's built, that builds that synapse in the brain that has the detail of that event. So they miss out on the nuances of the event. Same thing if you go into a museum and you take a picture of the Mona Lisa, they don't recall the image itself because their focus has been on capturing the moment instead of living the moment. So it's an unintended consequence. Of course, I'm not going to say that it's a bad thing, right? It fundamentally changes the way we work and we're much more efficient, but there are impacts to having that technology prolific in the way we actually engage with it. So the question I have is, when we start talking about this next revolution, we have these incredible power into now manipulating biomolecules, manipulating cells. What is the unintended consequences? Now, the science fiction version, sure, we have the potential for zombies. In fact, I read an article this morning about zombie mice, where we can actually turn on certain genes in mice and get them to aggressively attack both organic and inorganic materials by shining a light on it. And so there's a way to trigger that mechanism and create a zombie mouse. Now that's really cool, really powerful. Maybe something that can be weaponized. That's not so cool, maybe, depending on where you stand on the funding or the source of that funding. But I'd say in more reality, when we look at nanotechnology as the next evolution, we need to consider the unintended consequences of, well, how about nanoparticles? Where do they accumulate in the human body? Do they leave the human body? Where do they accumulate in the environment, in the ecosystem? When we talk about synthetic biology, what is our responsibility to make sure those things mutate in a way that we predict and that have the design consequences in there, or have some kind of mode where we're able to mitigate those powers that we're harnessing? So, I'm not gonna get on a soapbox. I don't want to be a naysayer in that technology. I think it's a very interesting and a hugely powerful technology that's going to advance medicine, advance the way we live and work, but we need to make sure that we have some kind of safeguard. So the speaker lineup will be myself giving a talk on nanofabrication evolution. Up next, we'll have Dr. Alec Nielsen. He's founder of Asimov, and he's an entrepreneur in residence at Pillar. He's coming to us from Boston, so he's going to be giving a talk remotely regarding genetic circuits. After that, we'll have Dr. Andrew Bond. He's the computation platform lead at Arzeda, and so he'll be talking about synthetic biology and building blocks. And then remotely from PNNL, he got trapped in the snow at the pass. We have Dr. Kyle Alvin out of Pacific Northwest National Labs, and he's going to be talking more about nanoplasmonics and their applications. So with that, I'm going to kind of shift gears, and I'm going to really talk about an evolutionary development. So where the nanofabrication industry is pushing, we're going to talk about scaling, stacking, integrating new materials in biology. So a little bit of background, promising not to do like a sales pitch, but I'm the director of the Washington Nanofabrication Facility. So it's a public access facility here at the University of Washington campus. We have both companies and students and researchers doing work in a joint facility. They basically rent time on equipment. We have about 100 process tools, and we're focused mainly on giving traditional fabrication equipment, and those are housed in about 15,000 square feet of class 5, 6, and 7 labs. We're very flexible in the materials that we're able to adopt, so we're very much focused on advancing new materials and integrating new techniques and methods of working. And then we're focused really on helping customers, whether they're both academic researchers or industrial companies, designing, fabricating, and then consulting on their prototype development and working towards commercialization. I think it's important to note that the companies that come from the outside the university, there's no IP entanglement, so it's not like doing sponsored research, but we treat everybody the same. Our goal as a staff there is to really help expedite people and get them up to speed and making new products and devices. So we do provide on-site training. We teach people how to make devices. That's our preferred model. We are able to do some light foundry work, so people can send us things to do some unit processes if they're not interested in learning. But there are companies that also do prototyping out of the lab, so if it's something that's not in your business model and you prefer to farm it out but you want more control, it is an option. Now, what differentiates a lab like ours from a commercial foundry is you have that flexibility. A commercial foundry is going to be focused on, here's our design rules, here's how we make electronics, design a circuit that works within those design rules. We're the complete opposite of that. Here's a tool set, you can try to tailor it to do anything you want. There are no rules. We throw the rule book out. The only thing we worry about is making sure that the customers aren't cross-contaminating each other. So some of our core technologies, we're focused mainly on sensors because we allow and we're permissive with a lot of materials coming into the lab. It's really hard to do CMOS in that kind of environment. So traditional electronics manufacturing really is tailored more for those traditional foundries. We do a lot of sensor development, so nano electromechanical devices and micro electromechanical devices. So the first example is a micromirror. We do some projected light technology, work with companies like Microvision. We have down below that quantum information systems. So we do a lot of nano silicon photonics, so small scale waveguides interacting in this case with a resonant disk. In this case, we're specifically introducing vacancies, nitrogen vacancies in that disk and looking at how it resonates and looking at quantum effects using traditional waveguides that are running basically 1550 nanometer. And so we are able to harness that technology not only to study quantum effects, but we're also able to biofunctionalize those materials and working with professors out of bioengineering that are using traditional photonics to maybe tag and look for a different analyte. So they're turning this really a physics device into a biosensor. And that's where we start seeing this confluence of different technologies. So by having that capability of having silicon photonics on a chip, they're able to do quick analytes over multiple biomolecules, or they're looking for certain acceptor sites to look for detection of certain materials. Advanced packaging is something that generally gets overlooked when you're in the research phase, but then when you want to integrate something, say like a biosensing device into a human body, all of a sudden the packaging matters the most. And so that's the area that I traditionally have been focused in, and looking at both advanced integrated circuit connections, but also making things that work in harsh environments. And I can't think of a harsher environment than the human body right now. So we work with people in consulting and coming up with engineered materials that help their systems integrate into into a sensing platform that works with the human body. So that's folks that are doing like neural implants, people doing spinal fusion sensors to look at the forces as the spine fusion takes place. We're looking into ways of sensing glaucoma remotely. And so looking at ways to embed sensors in the human body and have them last over the long haul. One last plug talk here, and then I'll move into the more technical end. We are part of the National Nanotechnology Coordinated Infrastructure. So there's a 10-year grant from the National Science Foundation. We're in our second year. We represent the one lab that's part of the Northwest National Nanotechnology Infrastructure. So it includes my lab, the molecular analysis facility that's in the molecular engineering building. And then at Oregon State University, we have the Advanced Technology and Manufacturing Institute. We have the Material Synthesis and Characterization Facility. And then there's a new building being built on campus that will be the Nano Engineered Systems Institute. So a bunch of groups of people working together to really enable the local communities to get their work done. Part of NanoES and the Clean Energy Institute is a new printed electronics test bed, and including that will be some nano imprint lithography, some roll-to-roll manufacturing, and so you'll see more of a convergence at the University of Washington where we're looking into molecular processing and scaling. Okay, part of our methodology, I'm obviously part of the MAKE group, but our mantra is to make, measure, model, and then also mentor. And so part of the workshop here, we have several of our students in the audience, and that's part of our mentorship, is to work on developing new engineers and technicians that work in the nanosciences so that the local workforce has a pool to draw from when they need those folks. Okay, diving into where we are as an industry. So the semiconductor industry has been facing some challenges lately. We have fewer and fewer companies that are at the advanced technology nodes. Right now, state of the art in production is 14 nanometer devices, and we're calling it a 14 nanometer node. And just as a sidebar, the marketing guys have jumped onto these nodes, and the nodes no longer have a resemblance to the actual physicality of what's happening on the chip. So back in the old days, when I started in this industry, it was 97. I'm dating myself, but I was right out of high school, so I'm not ancient yet. But basically, back then, the node meant what the size of our minimum gate length was. So it was the size of a transistor gate. And when the marketing guys took over, they just got onto these nodes based on how small they could actually print a feature, whether it had any semblance to what's happening on the transistor or not. And so it really doesn't mean the same thing. So if Samsung says they're shipping 10 nanometer, which is what they're claiming, they're going to get 10 nanometer chips out this quarter, and Intel's saying they're going to get 10 nanometer chips out in 2017, doesn't really mean that your gate length is 10 nanometers. In fact, the transistor pitch is still somewhere around the 50 nanometer mark, 55 nanometers. So that's point number one I want to make, is even though they're saying that, on this chart it kind of peters out at 20 nanometers, they're not quite apples to apples comparisons between these companies. The other part that I want to point out is it's getting harder and harder to sustain what was called Moore's Law. Moore's Law was not an actual law, but it was more of an observation by Gordon Moore, who was one of the co-founders of Intel, that we'd be doubling the transistor density roughly every basically year and a half to 2 years. So every 18 to 24 months, we'd double that. Well, in the last decade, that's slowed down considerably, and we've stretched it as far as 36 months. I know that seems like not that long, but for an industry that's constantly pursuing the next technology level, a 50% increase is considerable. But what isn't noted here is it's not really just the time, it's the extreme cost of getting down. So the limitations in our industry are really, how do you pattern, and how do you pattern light efficiently? And so we're still using light, but we have been focusing on getting the wavelength of that light further and further down into the extreme ultraviolet, which is now in the double-digit nanometer range. And it's a very unstable source and a very expensive, so we're using basically liquid molten plasma, that's a laser-based liquid molten tungsten, to generate this very low wavelength light in order to pattern a chip, but you're not getting a lot of light out of that, so you're having to amplify your chemicals, and we're using molecular engineering in that case to amplify the polymers and their response to light. But those systems and those methodologies are taking much longer to perfect and get into a place where they're actually manufacturable. And so that's dragging the timeline out, and it's also increasing the cost considerably. So one of those light sources now runs about $100 million, and the pieces of glass that we use to form the patterns that used to cost just a few hundreds of dollars are now costing on upwards of $10 million a set. So every time you want to change your design, it's going to cost you $10 million, and every time you want to upgrade, if you want to get into this forefront of technology, you're considering spending about $3 to $4 billion in just equipment plus your fab. So the cost is what's really eking out the people in the forefront. Now, there are a lot of companies that are hanging back, and they're absorbing technology, and they're staying at the 130 plus nanometer node. And those people are perfectly fine. They're making decent amount of margins, building things that aren't cutting edge, right? Building power devices, building communication devices that don't need to be pushed at really high frequency. So it's really the advanced computing folks and the memory folks that are really pushing that forefront. And everybody else has an ability to hang back and use things that are more antiquated, but that are working and that are a stable process. But Intel right now is the forefront still. Even though everybody's saying they're shipping 10 nanometer, they're probably the most advanced and the most stable in the process control. They're also looking at diversifying, right? So they're seeing the fact that the demand for chips and processors is starting to wane. So they're now opening their facilities up to foundry work. So they're actually going to be taking designs and be a production for hire, just like Taiwan Semiconductor has been doing. So the focus is the industry is changing. There are advantages in power consumption, but not really in speed at that size. The transistor density is definitely a factor there. And as we get more parallel processing on chip, that's still an advantage that those forefront leaders are carrying. Intel's kind of given up the fact that they're going to pursue the next node. So 10 nanometers, like I said, this year. The next node is 7 nanometer, but they're going to be introducing these demi nodes where they're going to try to extend the functionality and better performance without really shrinking the transistors any further. So they're introducing 10 nanometer plus and 10 nanometer plus plus. And again, I think it's more of a marketing thing. So the reality is it's getting a little sparse in the forefront. Part of the complexity of our industry is, back when I started in '97, we worked in silicon, aluminum, phosphorus, boron, arsenic. Those are the materials that we had in the lab. Nothing else was allowed. And as we've evolved, we've increasingly taken advantage and used more of the periodic table. So this shows in the blue and all the other materials, the newer elements that we're introducing into our production lines. When I say introducing in our production lines, a lot of those forefront companies still are afraid of things like gold because they're mobile ions and they tend to short out electronic circuits. So at that forefront, they're still very restrictive. Sure, they're going to include things like tungsten or new materials like hafnia as the gate oxide, but they're not going to be permissive with things like gold, silver, platinum, things that we see when we start introducing biomaterials. So that's where our type of lab exists in order to bring those advanced technologies to meet the new materials challenges that are posed by different applications that aren't purely process driven. So as a whole, our industry is focused on getting more functionality per unit volume, getting lower power consumption, getting faster processing. Faster processing has been a challenge, so that's why we went to parallel computing. And the reason for that is as we started driving the frequency of those chips further and farther, we were getting more and more drain currents going through the substrate. And so we were leaking a lot more power through the chip and not getting any function out of that leakage. And so that's why things haven't really advanced past that 3 gigahertz range, because as they start surpassing that, they find that the power consumption just drives up exponentially, and you end up shunting a huge amount of power and heat, which shortens your device life. And so that's why things have gone to the parallel approach. And that's why we still find value in shrinking that transistor node, is we're able to pack more of those parallel processes. But really, the driver has not been computing. We've gone to cloud-based computing, so people aren't having their own super computing farms or anything like that. And so our focus has shifted also towards the mobile applications. So if you tear down your cell phone, you'll find that things have gotten more into modules. We're looking at efficiencies in fabrication and trying to cram as much function per unit volume as we can into these cell phone packages. And really there's two reasons. We want smaller devices, and we also need to make more room for the battery, right? As we add functions, the consumption of energy goes up, and so we need to maintain as much battery capacity as possible in that fixed package, right? So what gets shrunk is the electronics to the extent possible. And so if you look in your current state-of-the-art phones, you're looking at 10 to 15 of these modules now. And inside, if you tear down those modules, to see what the lower picture shows is a wire-bonded chip stack. So this is where we actually thin our chips, we stack them up, and then we connect them with all these wires on the edge. And it looks like a rat's nest because that's what it is. It's a rat's nest, and it's really hard to do, but it's actually fairly low cost. And so that's where these module manufacturers have really put the forefront of our efforts. And it works really well in mobile computing, but it's not enough. We keep adding the functionality. We add more chips to that chipset. And so we've done things like now embed the chips. We've consumed the front and back of the circuit board. And so we've run out of real estate on that main board in your phone. And so now we're looking at embedded chips and passive devices in the inside of the printed circuit board. So we have, as you look at the bottom picture there, that's where we have some prepped areas for flip chip or wire bonded inside the laminate. We then introduce the laminate materials and we put the circuit board together. You'll end up with what looks like the top picture there. And then you'll put your other chips on the top and bottom of your motherboard. Now, you're going to put your highest reliability chips in the inside of the board because once you sandwich that together, you can't rework it. So if your chips on the inside are bad, you have to throw the whole module away, and that's a huge waste. So that's one of the downsides to having this approach. The other one is you're severely limited on the input and outputs because you're still fanning everything out. So you're pretty restricted in what you can place on top and below that chip. You can't do things like have high heat producing chips inside that sandwich because it'll start to buckle the materials and cause delaminations and other failures. Well, we won't talk about engineered failure because if anybody has a cell phone that makes it to 3 or 4 years, it's a feat of engineering now. We used to shoot for 10-year life, and then we decided to do away with that because it was costing us business, right? But anyway, this is what you'll see in state-of-the-art cell phones right now. If you're looking at higher density connectivity, then you need to go to a more advanced approach like 3D integration. The picture that you see here is a chip stack of memory chips. Okay, so they have these vertical pipes that are connecting all these different strata, and each layer that you see there is a different chip or wafer that's been stacked up and then connected vertically. And this has been hugely successful in the memory market. So if you have flash, you've seen your flash capacity keep going up, right? You're now getting 64 gigabit flashes. So we're able to get a huge amount of density out of memory stacks for a couple reasons. One is all the memory guys got together and they came up with a standard. I know that seems crazy or seems normal for certain industries, but in our industry, the team dynamics aren't there, right? Different companies don't really play well together, right? It's highly competitive. But the memory producers got together and actually standardized an interface. And they actually have cross-compatibility. So they helped each other out because they found that they had a healthy market segment there and they could all play in that swimming pool together and do well. So that was one of the things that enabled the 3D stacking of memory that we haven't seen elsewhere in the industry. The other part of it is it's a scalable architecture. So we can have all these different layers of chips, and if I have a bad layer, all I have to do is kill one of those layers. I can just blow a fuse out and ignore that layer altogether and just program the controller chip to ignore the bad layers. So I can produce and bin with different chips. So if I have 2 bad layers, then it's only maybe a 16 gigabit chip that I can ship and sell. But if I get all the layers, maybe I can get a 64 gig chip. And so they're able to economize and receive profits off of things that are maybe even just functional partially. So that's a key advantage when you have a common infrastructure. The other part is they can just do a wafer scale integration. So they stack all these wafers up, they bond them together while they're a wafer, and then they drill and put the vias in, or the vertical interconnects at the end. And that's hugely cost effective, okay? The comparison would be heterogeneous integration. That's where my research worked. So I spent 10 years in the Defense Department working on this technology. And of course, we took the hardest approach of saying, taking a processor and marrying it to a memory. The thing is, there are no standardized IOs. Companies, even though we were the federal government, wouldn't tell us where we could and could not put metal vertical connections. So they don't want to tell you what's inside their chip or give you their design, even if you are coming from the federal government. They certainly aren't going to tell their competitors that. So we were limited to where we could put connections out at the periphery of the chip, which means we had to fan in and fan out all the wires from that. And so that's still a limiting factor, right? We can only have so much connectivity if we're not able to put things within the chips. The other part is we just had yield. So we have all these commercial chips that come as chips, and now we want to do things back in a mass production regime. So we're having to take loose chips and put them back together and glue them down onto a wafer. And when I say glue, I'm using that term very loosely. It could be bonded covalently and form a solid bond or a permanent bond. They could literally be glued with an adhesive as well. And those could be temporary or permanent adhesives. So there's a lot of work there to get the things to line up. And if you have two different size chips, as you see in the picture here, it can be quite a challenge to get all those chips to line up relative to their carrier substrates or their temporary holder, and then having them align to each other, and then doing that within a few microns of tolerance. So incredibly complex technology, and a huge slew of materials and machines that you have to develop in order to enable that. And so that's why that has been very slow to come to market. The other reason it's slow to market is the prevalence and materials challenges that we've had with these through silicon vias. So a via is a metal interconnect between two layers, and it's just a plug of metal that's a wire that's going up and down, okay? So the challenges in there is that you have to do really thick lithography, so you're limited on what you can resolve. You have to do a process called deep reactive ion etching, where you're actually boring a hole down into the silicon itself. In fact, when I was talking to Jimmy before, they were using a laser to do some surface analysis. We were trying to do laser drilling, and that had like huge amounts of slag. So we had to develop new etch techniques in order to get a hole through a chip without having a big plume or something that we had to clean up on the surface. You then have to isolate that hole from the substrate from the metal. So if you have a metal plug going through a piece of silicon, again, silicon is a semiconductor, so there is a propensity for that metal to migrate into that silicon, and then you can start shorting to each other. So if you have two wires next to each other, there's a potential for them to start shorting out through that substrate to each other, or even just having crosstalk to each other using high-frequency communications. So one of the limitations there is we need to put some kind of isolation material. So one way that we make really good insulators is by heating our samples up to about 1200 degrees, introducing a little bit of water vapor, and then silicon forms a really great native oxide, and we can diffuse some of that oxygen in to create really high quality insulators. The problem is when you're doing 3D electronics, you already have CMOS circuits there, you already have metals on those chips. And so they can't handle 1200 degrees because you'll melt all the metal lines that you just paid a lot of money to get. And so we have these thermal budgets that are imposed on us where we have to get conformal coatings, we need high quality coatings, they need to perform just as good as a thermal oxide, but we have to do it at a much lower temperature than what we're used to doing. After we cross those three hurdles, we then need to get a barrier metal down the hole, and that helps prevent that metal migration through. So typically our industry uses tantalum or tantalum nitride or titanium nitride as that barrier metal that prevents that copper from migrating in. And then we have to coat it with a seed metal to get this hole ready for electroplating. So typically we're using copper. And some of our advanced research at the lab, we're working with other materials like cobalt, ruthenium, different things that we can use to seed it. And in order to get metal down those holes, if we use really big holes, we can just use traditional things like sputtering, where we just shoot metal ions everywhere and they eventually coat the sidewalls, and then we can do electroplating. The problem is we want a lot of connectivity, right? So we can't live with a 100 micron diameter hole. People are pushing us to be at like 2 to 5 microns. And so as you shrink things down to 5 micron diameters, but you're still 150 microns deep, getting metal down a very narrow hole or pore becomes a substantial challenge. So we're using new techniques like atomic layer deposition in order to get those materials and metals down in the hole, and then trying to count on things like capillary action to get those plating chemistries down into that hole and do it in a way where we don't form large voids. So if you look in the picture, there's an example of a very small void. That one wouldn't be a killer defect, but if you have things like bubble formation, if you get any trapped gases in there, or impurities or large biomolecules, so a lot of times we're using different molecules to create favorable plating conditions, we can block the plating in those holes. And if you have one bad via, it's possible that you kill your entire chip. So it's a really critical operation and a very challenging operation. After we do all that and we get through plating, which is the easy step, we then have to take the excess material off, and we use a chemical mechanical polish to cap those. And then after that, we do the post-processing where we distribute out those signals. So you can see it's a very complicated thing to do just one aspect of a 3D stack. So because of its complexity, people have gone to something called 2.5D. And this is where we want to get the performance of having 3D circuits, but we're willing to sacrifice a little bit of that performance for ease of manufacturing. And so the example I have here is some work that we did with IBM when they were IBM. They're now Global Foundries in that lab. But basically, we had a quad FPGA, so we had 4 FPGAs that all needed to talk to each other, and had one of them was a master control chip. And we needed really high frequency communications between those chips. So we were able to produce a carrier using silicon technology. So we used silicon, we created all the wires between those chips on top of that silicon using traditional techniques. And then we took that module and then put it on a co-fired ceramic interposer, and we were able to get a supercomputing type functionality out of that. The problem with it is it was extremely costly. It was still substantially thick. It was well over 1 millimeter thick, and it still required quite a bit of complex processing in order to make the stack up. The thickness was one of the issues we had, and going back to, again, our mobile computing applications for mobile devices, that's a real fundamental problem. So I have a cartoon mock-up of just a slice of one of those 2.5D systems. So we had these TSVs still going through a carrier substrate. We had electronic components, both memories and ASICs, or in this case the FPGA, sitting on that common carrier. And then we had these passive components. And if you look at the scale of the devices, the passive components, that's an 01005, which is the smallest surface mount component that's available commercially still today. So you can see that the chips are not really the issue. The fact that we have passives embedded on this device increased the thickness substantially, and the fact that we're using a full thickness silicon carrier adds about a 0.5 millimeter thickness. So we can thin those down. Our industry is getting really good at thinning components, so the chips themselves are thin now, somewhere between 70 and 150 microns, but we were proposing to also thin the carrier itself. And so we're able to take a substantial portion, or about a 0.5 millimeter of that thickness, by removing the handle completely and just using the metal and the dielectric that we put on top of the wafer as the interconnect between the chips. So we're able to get things down to sub 15 microns or so. In fact, we've done things as low as just about 15 microns as far as the interconnect goes. And in this case, you lose the rigidity of that system, so you have to count on this traditional epoxy overlay to become the rigid substrate. So it's quite a challenge to get an epoxy that has a different coefficient of thermal expansion from silicon to match and not compress and cause contortion. In fact, our first few attempts at this, when we went through, we spent 6 months doing this. We got our samples done. Everything looked good. We put our stencil solder balls on top of our sample, so that the bottom of the chip there in that picture is the last step. We stuck it in our traditional reflow oven. We heated up that plastic substrate. It warped, and all our solder balls ran all over and shorted and bridged, and we lost 6 months of research. So, just one oversight on our end cost us substantially and dearly. So mitigating stress, and that's, again, where the folks that are able to start manipulating the molecules and working at advanced polymers and helping us get things that are closely matched, that's where these convergences of technologies are really come into play. Well, even though we managed to work out all the bugs, the next layer of thickness there was we had about 75 to 100 microns of thickness consumed by these solder balls. And so we were able to replace solder balls by introducing a standard process called NEG. And I see one of our audience members is from a company working on new NEG technologies. We were able to remove the solder balls and replace them instead with a thin layer of nickel and then a flashing of gold. And then working on surface chemistries and surface enhancement in order to bond gold to gold interfaces together and remove the solder ball entirely. So we were able to reduce the thickness by another 100 microns, and now we're literally splitting hairs as far as thickness goes, but it's on our way to a thinner module. The key component here is still our passive devices are dominating the bulk thickness of this device, and that was a severe limiting factor. So we started getting into embedded passives. Okay, so can we make passive devices that are part of our substrates or that are very thin? And so we were able to reduce the resistors using traditional nickel chrome or silicon chrome thin film resistors. We were able to build these very novel inductor loops to create transformers on chip. But we were still really having a hard time building really high value capacitors. So that's where we started looking outside the box, getting away from the organic or the inorganic materials and looking towards organic systems. So we started looking at, can we interface and get biology onto the chip and start leveraging the fact that we can manipulate some of these biological systems and get them to do things like form a battery or capacitor. And so we started working with, in this case, tobacco mosaic virus. So we have a virus that has a nice tubular shape, and we can biofunctionalize one end of it and create a binding affinity to a metallic binding site. And so we can self-assemble these little viruses, and you can see here these are collecting on the surface here, and they have a nice long cigar-shaped kind of structure to them. And if we take our traditional fabrication techniques, we can make a bunch of pillars and then functionalize those and then get those viruses on there, and so we can get these huge surface area enhancements. And then we take things like our atomic layer deposition and we can coat those viruses. So you can see here this virus is the core of this shell. It serves nothing functional other than being a scaffolding to build on, okay? So it has no function. We put a titanium dioxide coating, we then put a nickel coating, and then we can put another titanium dioxide, and that forms our dielectric barrier. We can then introduce an electrolytic solution, and we can form either a high-value electrolytic capacitor, or we can take another set of those electrodes and create a battery structure with two dissimilar metals. So we're able to get now the high density and functionality that we need. We're also able to address things like different power levels on a chip, so we can actually create these micro batteries on chip. So it's a way to enhance that area and also integrate new materials, in this case something that we borrowed from the biological community. Present efforts in this field come back to that pushing the edge of technology. So not everybody can afford a 10 nanometer fab. So one of the things that DARPA is currently proposing and taking proposals on is their what they call CHIPS. It's a Common Heterogeneous Integration Intellectual Property Reuse Strategy Program. And only DARPA could come up with an acronym to fit CHIPS. But basically what they're saying is let's build little chiplets at that high technology node. Let's leverage that 10 nanometer technology that Intel has spent literally billions of dollars developing, and let's create small functional blocks. And so instead of having these custom ICs that take 18 months to design, then we go and fab them, and it takes half a year to a year to get those chips back, and then we find out that we want to do another redesign, and they have to buy $10 million more of glass, which is very problematic for something like the defense industry that only needs 10,000 chips, right? It's really hard to amortize that $10 million mask cost over 10,000 chips. So that's where you get a $100,000 toilet, and it's because you're spending $500,000 on one chip. So the way that they're looking at it is, hey, let's take that technology, let's use these little functional blocks, let's use ALUs or arithmetic logical units, or let's use your small memory cells, and let's build these little chiplets, these small parts or subchips, and then use a common interface like that 2.5D technology to marry all those chiplets together. And that way we can create custom engineered systems with high throughput and low cost, but still leverage that advanced technology that's been pioneered. And so that's where we're seeing the convergence of this industry going, is leveraging that technology. We're also seeing more and more of IPDs come into, so integrated passive devices come to market as the frequencies go up. So as we're looking at 5G as the next cell phone node, the values of those passive devices that are used for like cell phone filters, and that's what you see here is just an LC filter that we're able to work in the 25, 30 gig range. Those are ways that we can now start getting these passive devices that are on chip to actually make sense, and they're actually functional at the target frequencies we want. So we're seeing that all kind of converge at the same time. Now, it's not a slam dunk. The one difficulty of integrating all these little chiplets is that we need better precision in our placement technology. So when you look at a chiplet, right now, state-of-the-art pick-and-place tools where they actually pick up a component up and place it down mechanically, you can do about half micron, or 500 nanometers alignment accuracy. And if you're targeting smaller and smaller interconnect, because you don't want to waste that huge amount of volume with a bunch of vertical connections, we really need to do better than that. And so there's a throughput issue with that, with mechanically placing them. There's an alignment tolerance issue, so there's some tool development that needs to be done there. But there's also a throughput issue. If you're doing that serially, it's going to still be very cost prohibitive. And so we're looking at new technologies where we're doing self-assembly, where we're actually functionalizing or putting like a magnetic dot on a sample and then allowing things to self-align. And that way you can do parallel population of all these chiplets. So you can functionalize a certain segment, run it through, float a bunch of little chiplets on a little bit of a bath of water, as you see in this right picture. So we can float them in there, they self-assemble, they latch on, and then we can go through a process that allows them to be permanently bonded. And you can see that's the result of some of the collaboration work between one of our labs at UW and Intel. Finally, I just want to talk about the future. As we see this confluence of electronics and biology, we're also starting to mimic some things that we're learning from biology. So this is an example of a lotus leaf. The lotus leaf has a super hydrophobic surface. So you can see that water sphere, that droplet just sits on the surface. It's not actually making contact. And that's what it looks like when we do the surface analysis under the SEM. So you can see that you've got all these little tiny pillars. And so what we're able to do is start mimicking that biology. And so we take our traditional fabrication techniques, we can create that kind of topography and create super hydrophobic surfaces. And if we put in things like gradients in those surfaces, we can actually manipulate the way that droplet forms. Well, so what good is that? Okay, we mimicked a lotus leaf. Well, this is some work that's coming out of my boss's lab over at the university for self-cleaning surfaces. So we're using a water droplet there to clean the surface, and these are little sand particles that are being swept up. So we're just vibrating. Imagine using your cell phone, the piezo that's in there that vibrates your cell phone to let you know you're getting a text message, using that same function to clean the surface of your device. And if you want to have an automatic self-cleaning surface, you can do things like maybe make it get cold, right? Put a cold plate on there so it condenses a water droplet on there, and then just manipulate that water droplet to kind of go over the surface. And so every night when you go to plug in your cell phone, your screen cleans itself, So maybe not super practical today, but that's the kind of area that we see our industry trending. So very evolutionary, not quite revolutionary, but still those incremental improvements. So I'm going to end just with acknowledging, the work was supported partially by the National Science Foundation, highlighting some of the work of Carl Bueringer at the University of Washington, Dan Ratner, who's doing a lot of our biosensing using photonics, and then Reza Ghazi, who I collaborated with to do the tobacco mosaic virus work. So thank you very much. I appreciate it. You got it? Okay.
Really bright up here. Okay, my name is Andrew Ban. I'm from RZeta, as Mike graciously described earlier. I'm the computational platform lead there, and I'm going to tell you about the reality of nanofactories today. And so I'm actually going to lead off with an interesting observation from sort of the virtual reality in the IT world, and I think this is an observation that has probably been made by several people. I heard it the latest from the work of Jerry Lanier, who was an early VR pioneer, and that was the fact that back in kind of the late 80s and the early 90s, everyone thought that we would be interacting with the digital realm nowadays and the phrase was kind of being jacked into the net. Right, and so this was kind of the concept of having the big goggles and the various kinds of suit hardware, and then maybe possibly cables leading into your brain directly from the back of your head. And so obviously this hasn't really come to pass yet, and the reason, and people are working on it, but the reason for this is because the whole man-machine interfacing stuff is really, really hard. In the meantime, the whole concept, the dream of being continuously checked into the net actually did come true, but in a different way. Right? And so that's through the high-density interface between our visual system, the eye, and the smartphones that everyone is using nowadays. Right? So everyone is constantly connected, everyone is constantly interacting. So we're all living in kind of both the real space and the virtual space at the same time. So likewise, when people think of factories, this is the kind of thing we think about. And so this is a photo of the Tesla factory down in Southern California, and so what is it? It's robots, and it's high-speed assembly lines, and so things are being put together with extreme precision and speed, and so analogously, when our brains then start thinking about things kind of reduced down to nanoscale, what is it again? It's these really tiny, cool robots, right? It's nanotechnology, sometimes called nanites, in kind of the popular writing or the science fiction writing, and it's these incredible things which can self-replicate themselves, which can build things, maybe build an entire human, and maybe replicate that pot of Earl Grey tea that Mike was talking about earlier. So that's also a really hard problem. And so people are working on it, and I think we've seen some really incredible advances over the recent years. But you've got a lot of problems to think about there, right? How are you going to encode the command and control logic down at that level? What's the power source going to be? How are you going to make these things communicate? And what are the advanced behaviors actually going to be? But what I'd like to put forth tonight is kind of analogous to the VR observation, which is that there is an alternate implementation of this, which is actually available today, has been available for quite some time, and that is the biological cell. And so the cell itself is quite an incredible chemical molecular nanofactory already, highly evolved, highly optimized for sustaining life. And just to kind of give you a rough I would say, perspective on this, I'm about 1.7 meters. Cells typically are 1,000,000 times smaller than me, anywhere from 1 to 30 micrometers. And then the actors, or the robots that are actually doing all the work inside the cell, are then 1,000 times smaller than that. So we're truly kind of at the nanoscale. So your 37.2 trillion, which is kind of the most recent accurate estimate, I guess, cells, as well as the 30 to 40 trillion bacterial cells, which are living in you and on you, as well as every single other cell on this planet at the moment, every second, is engaged in this set of life-sustaining chemical transformations called metabolism. And what I've shown you here on the slide is basically a graph of a metabolic network or metabolic map of most of the primary components of metabolism, what we know about it. And so this has been figured out over the past century by the hard work of many scientists. And so you're basically making all sorts of molecules to be able to sustain life. And so now that we know all about this, the question is, can we actually use this framework and then tap into it from an engineering standpoint to actually make the molecules that we want to make? So just for purposes of illustration, I'm going to zoom in a little bit closer to this map to let you see a little bit better maybe what it looks like. Oh. Do you guys see that at all? Oh, I'm sorry. Maybe the next slide will show up better. I didn't notice that. Right, so we know a lot about metabolism, and so I'm going to zoom into a center section called the citric acid cycle. Does that show up at all? Okay, that's a little bit better. You're not able to see everything, but hopefully I can talk through it. So this is known as the citric acid cycle. And so from biochemical cellular standpoint, this is important to the cell because it starts kind of from the left-hand side from a molecule known as acetyl-CoA, goes through 8 different chemical transformations and ends up at oxaloacetate at the end. And so along the way, what you're doing is you're actually generating, basically capturing chemical energy in order to be able to shunt it downstream to create ATP, which is the energy currency of the cell. And so that's important for the cell for life. But for us, from an engineering standpoint, this kind of map and this kind of diagram is really interesting because it says, oh, well, I can make oxaloacetate from acetyl-CoA in this manner. So knowing what I know now about this part of metabolism and all the other parts of metabolism, all the other chemical transformations, well, what else can I do, right? Can I be able to play with this? Can I be able to engineer new things and make the things that I want to be able to make or the things that humans are more interested in making? So that's kind of the first thing you need, right? You basically need a route. You need to know what the chemical transformations are. You need to know how to get from A to B. And so the second thing that you actually need to know and be able to take advantage of the cells in Nanofactory are then the actual actors. So if we use the analogy of the cell as a factory, and this route is essentially the assembly line of how to make what we want to make, we also need to be able to know and engineer what the actors are, what the robots are, right, in sort of the high-tech factory type of standpoint. And what we have then, through the hard work of many scientists, we know what these things are and what they look like and what they do. And so this is the set of enzymes, the set of 8 enzymes that comprise the citric acid cycle. So you go from the top, well, you can't see it's being cut off, but it goes so 1, 2, 3, 4, 5, 6, 7, 8. And so enzymes are basically proteins that help catalyze these chemical transformations. And you can see there are varying types, varying sizes. Some are stuck in membranes, some are free-floating. And then you can have things of collections of proteins and enzymes that are in superassemblies, like the number 4 there, kind of smack dab in the middle. That's actually not even all of it. The center component is really surrounded by 24 different subunits. And so through a lot of science, through a lot of hard work, we now know something about these enzymes, and we know that we have the possibility of engineering them. So then the 2 components that we need to use to make new molecules with synthetic biology, the first are the routes, how do we get from A to B? And the second is, how do we actually get and engineer the actors, right, these enzymes, which will actually make these chemical transformations. So the promise of this is actually very, very large, and the impact is potentially gigantic. So if you look at, so this is kind of a slide about the scale of the spaces of molecules and products that can be made. And so if we focus on just the man-made products for a second, just in terms of dollar amount, this is about, I think, a $1.3 trillion market as of 2014. The thing about this is that most man-made products they're still derived from oil, right? So like the lacquer on this wood desk, all the chairs you're sitting on that are plastic, right? It's all made from oil, and so this is not such a good thing. And so from a sustainability standpoint and a planetary standpoint, we'd like to move away from this. In terms of properties and cost advantages, you can see that the space of man-made products is actually very small relative to the whole space of biodesignable products, and it also doesn't really intersect necessarily with the existing biological products that are made by cells. And so that means that we need to really engineer cells as nanofactories to be able to produce what we want to be able to make. It doesn't exist already, right? So the cell doesn't have to make jet fuel, for example, to survive. This ends up being a very large computational or combinatorial problem, I should say. Unfortunately, you weren't able to see the whole metabolic map, but there are thousands and thousands of reactions and enzymes on that are actually doing that work and making lots of different kinds of molecules. And then if you consider this particular diagram, which is the space of all possible addressable molecules, we're talking about a million times larger. And so what you have is a very large combinatorial problem. And this happens to be something that computers are very good at solving. And so that's actually what we've done at Arzeda. So what we've been able to do is we happen to live at a very nice intersection in time where, number one, the cost of computing and the amount of computing you can address is rapidly increasing for less cost every day. The second trend is the fact that the cost of actual DNA synthesis is dropping, so we can access greater and greater amounts of DNA. And the third is the total amount of biological data is just growing. It's kind of mind-boggling each year. And so what we can do then is we can funnel all of this into a computational and experimental platform that we've built to be able to design proteins and design pathways, and I'll describe that to you today in my story. And to really being able to get designer functionalities. And so you'll get custom nanofactories out of this to be able to create the kind of molecules that are important to you or important to mankind. So aside from computation, as I alluded to, we marry this to a downstream high-throughput lab platform, right? So we make our calculations and our predictions, and then we obviously are a product company, so we want to test everything that we make, just make sure that actually works, and then we'd be able to optimize it. What I'd like to do is then talk to you today about the two primary components of the beginning of this technology stack, which I kind of alluded to before, which is number one, how do I find the routes? So how do I build the assembly lines? And then how do I actually build the robots and the actors? How do I build the enzymes? So the first topic we're going to be hitting on today is a software technology that we call Skylax. And this is how we engineer and find novel metabolic pathways. The classical way of doing this, of finding if I have a starting molecule and a target ending molecule, how do I get the chemical transformations that go from A to B, is basically for a scientist to sit down, crack open their biochemistry textbook, crack open the organic chemistry textbook, have a bunch of recent literature in front of them, and manually write down and figure out what all the transformations could be from my starting molecule to my ending molecule. And as you can imagine, this is kind of a very arduous process, potentially very error-filled. You might miss a lot of things, but historically, this is how people have really addressed this problem. But if you think about the total amount of data that we have now, this is accessible via computation. And so at Arzeda, we address this a different way. We basically take two sets of information. And the first set of information is the knowledge about all the currently known enzymes and reactions, essentially that metabolic map that unfortunately you couldn't see, but that and then plus all the other reactions that we know about. We gather all that data, we encode it all. And a second set of data, which encodes what the types of reactions and enzymes that nature could actually do, but hasn't done yet. We combine these two types of, sets of information, kind of the known and the possible. And then what we do is we do essentially what you can think of as a graph construction or graph search on top of that data. And that way, we're able to get all routes going from my starting point to my ending point. right? So we get basically a complete set of possible pathways from the start to the end. It's always reproducible, so it's not dependent upon the scientist that's actually doing it, and we get this. We can get these routes much faster than if it was someone just sitting down and writing these things out. The key thing about all this is that on this plot on this slide you have reactions on the right hand side, and so 3 sets of basically chemical metabolic pathways. The one on the rightmost side and the middle one are routes that you can think of as composed of as sort of known reactions, known things that nature already does, but I kind of mix and match them to do something else, do something that I wanted to do. Now, the route on the left is completely new, because not only does it use enzymes that currently exist, it includes enzymes that we can engineer. So nature doesn't have these yet, but we are able to make them. And I'll describe that part of the technology stack a little later, but that's kind of the key thing to keep in mind. It's that we can access not only what nature has given us, but we can also access things that nature hasn't even thought of yet. Because it never had to, right? All the chemical reactions, or most of the chemical reactions that are involved, naturally are again for sustaining life, right? And not for making nylon or jet fuel or something like that. So we can run this set of complicated calculations, and what we get out at the end is something like this. Basically, what we have here is a subset of the possible paths for a proof of concept we did for an amino acid called methionine. This is a $1 billion market currently, and it's primarily made for various reasons chemically as opposed to biologically, industrially, I mean. So basically what you see here is you get lots of different kinds of routes. And the total number of routes that we get out for any particular problem can be hundreds of pathways all the way up to millions of pathways. And so we need a way of actually sorting down the possible particular routes that we want to use. And so what we do is we apply a set of theoreticals and computational filters to find the most the nicest routes, essentially, by various different factors, and we'll select one of them. And so then we will take this and we will move it downstream into 2 parts, sort of the protein computational protein design and engineering, as well as the wet lab. And at the end of the day, if we have good luck and we're good at our engineering, we get a complete novel pathway that goes from a starting molecule to an ending molecule. And so we've actually recently done this. We were happy to announce kind of one of the showcases of this particular technology is applied last November with our a DARPA-funded grant. And so we've basically shown that this type of methodology actually does work out. So if I go back really fast to this part of the slide again, those blue dots in the middle that I have highlighted for kind of illustration purposes, let's assume that these are enzymes that don't actually exist in nature. So we can't just grab them from some organism, get the DNA and then express the protein recombinantly, express the enzyme recombinantly. We actually have to make this enzyme. And so how we do this is as we use our technology, computational protein design technology stack, which we call Architos. And it works as follows. So what we're actually doing is an in silico screening of protein sequences. And so proteins are linear chains of amino acids. There are 20 different amino acids, and sort of a nice way of thinking about this sometimes conceptually is that these are a linear chain of beads on a string. And what you want to be able to do is so that each bead has one of 20 properties, and this entire thing is then going to fold up into some configuration. And as far as proteins and enzymes are concerned, sort of geometry is function and function is geometry. So basically, if your protein is able to take the shape that is necessary for the function, then it will have that function. And so what then you need to do, right, is you need to figure out the most optimal sequence, the most optimal set of amino acids at each position, which will give you that fold for that functional enzyme or functional protein. And so the way you do this computationally is you basically have an encoding, which I'll describe a little bit later, and you evaluate the goodness of fit of that sequence on top of basically that particular fold or that particular conformation you want it to take. That evaluation then is done by what's known as a score or an energy function. And what you'd like to do is you'd like to have the lowest possible score or lowest possible energy, and that will drive that particular protein into folding into that shape. This is then basically a search over very high dimensional space, right? So if you have a protein which is 300 amino acids, then what you're looking at is a space of 20 to the 300, which is very, very large. I can show you this really briefly. This is a movie that'll play. It's kind of the kind of design process that we do. And so let's see, is this playing? Let's play. So this is, so you'll see here initially, actually, this is the protein backbone and then kind of the rainbow color, and this is the stochastic search that's being done over the possible amino acids at the different possible positions. And what you're doing is you're searching for, again, a set of an amino acid sequence which will stabilize this particular conformation, this particular fold. Kind of the various different motions that you're seeing are different stages of this particular computational protocol, where you have some large movements and you have some small movements. And so you can see here it goes along for a while, and eventually it will settle at a particular minimum, should be soon, which is here. And what we've actually done, or what was done with this particular protein, which is called TOP7, this was work that was actually done back in the lab, back in the university lab, is that the designed protein's conformation experimentally matches what is actually seen when you visualize or image this particular protein. If we move on really quickly, so just a little bit of details about how this goodness of fit is actually evaluated. So basically what we have here is we have an energy or a scoring function which is composed of a series of terms. Some terms capture the reality of the physics, right, and the interactions of the proteins. Others are knowledge-based and they're derived from data. And basically the sum of all these terms together implies the goodness of fit of this sequence on that particular protein fold. And so the interesting thing about this is that up front, sort of a priori, you don't know what the weights are for all these terms. So you don't know how, which one is more important, which one is less important under which situation. And so you need to be able to assign these weights, right? So the W term here I've circled in red. And so what we do is we use a machine learning approach using basically training this function on naturally known structures and naturally known sequences. And do an optimization such that we basically arrive at a goodness of fit function which is reasonable and which is well performing for our purposes, which is the design of protein structure. And then we're able to use this to be able to design and build and test new proteins and enzymes. Here we go. So this particular approach has been industrially validated at RZeta, so it works quite well under different contexts. So we've done both basically pure enzyme design projects as well as sort of the more molecular manufacturing pathway enzyme design projects. For example, on the enzyme engineering side, we worked with Pioneer Hybrid. They're a division of DuPont now, and they are the ag biotech division, and we've designed new crop traits with them successfully. We've also worked with a local company called Stratos Genomics. They are a next-gen sequencing company and basically readout of DNA, and we've helped them design new enzymes for that purpose. And then on the manufacturing end, we have successful collaborations with Invista and Mitsubishi Rayon. So Invista really for working on precursors of nylon. They are the brand holders of spandex and lycra. And so hopefully in the future you will be able to get your nylon from a clean biosource as opposed to from oil. And Mitsubishi Rayon then obviously is a chemical polymer fiber manufacturing company. And so we worked on some of the molecules with them. I think that's, I'm about to close, I've hoped that I've sort of told you some or described some of RZ Data's technology today and showed you the fact that molecular nanofactories, molecular manufacturing really is something that is not really a dream. It's something that we've been able to attain via the hard work of, I think, a collection of many people. We use high throughput computing to really be able to access these types of spaces, and I don't think you could do it in any other way. It's very difficult otherwise. The combinatorics are just too large. I think I'd like to close with kind of more of a conceptual slide. I was asked by the organizers to kind of predict maybe 10 years outward where things might be. And I feel like a lot of things I say here are probably going to dovetail pretty well with what Michael has talked about earlier. Basically what we're going to see is that some seemingly incremental gains are going to compound and create some revolutionary feats. So things kind of have a way of compounding and kind of sneaking up on you. And personally, I feel like the primary thing that's going to occur, that's going to cause this, is really speed and accuracy, really speed. So faster prototyping, faster implementation. And if you kind of take the analogy of what's happened in the IT space with ever faster processors and ever greater amounts of bandwidth, I think you're going to see kind of for synthetic biology field a similar kind of thing happen. And I think that one of the interesting things that's going to enable is kind of this game of what if. So right now the engineering timelines, even given what we've been able to achieve, are still quite long, right? And so to be able to kind of prototype and then get out enough sample of the molecule that you're interested in, you're still talking a year or two, maybe more. That's just for one molecule, right? So imagine if someone is able to come along and say, I want to make my plastic stronger, right? Or I want to make a softer fabric. What can you do for me? Well, in the material science realm, generally it's very hard to predict the properties of new materials until you've actually made them. And so you've got several issues here. Often it's very costly to make samples of some of these new things. And sometimes you can't even make them, right? They're just not accessible by the organic syntheses methods made today because, for example, they're not specific enough. And so the hope then is that we're so fast, right, that we can say, okay, well, in a few weeks, in a few months, we can have samples of 100 to 1,000 molecules to you, and now you can begin to just play with them, combine them in all the sorts of different ways you want to be able to use them and figure out what the actual material properties are, and hopefully get you the kind of performance that you want out of that material. So from a technical aspect, I think we're also going to see a greater selection of chassis usage in synthetic biology. Right now, a lot of people use very standard organisms that are easy to engineer, things you've probably heard of like E. coli or Saccharomyces, so baker's yeast. There are some sort of exotic microorganisms that are doing some very interesting metabolism and very interesting types of reactions and that survive, for example, at sea vents, which hopefully we'll be able to take advantage of because they allow for additional kinds, potentially, of chemical transformations. We might see some minimal cells. Some of these have kind of the beginning of this has been reported in the literature, I think, earlier last year. So cells that in which you have kind of a very, very basal level of survival. It's not a noise that's interrupting the kinds of manufacturing that you want to be able to do with your cell. And then we're also probably going to see some microorganism communities. But the last thing that I think is going to be the most interesting and probably the least predictable, and which Michael already touched on, was the meshing of biological and non-biological techniques. And so I think people are going to begin to discover some pretty creative ways to combine what we're doing in the synthetic biology field with other things, maybe biobatteries or something to that effect. I think that's almost 30 minutes, so I'm finished here. Thank you, everyone, for listening. If you have any other questions, you can ask them now, or feel free to, find me at the end of the session. So, thanks.
Hey, Kyle, can you hear us? Can you hear us? Kyle? Kyle? Can you hear me okay? Can you guys hear me or see my screen? Hello? Can anyone hear me? Hello? Testing. Hi, this is Kyle. Can anyone hear me? Hello? How about that? Sounds like we're experiencing some technical difficulties here.
There, you got it.
Can you hear me okay?
Yeah, we can hear you now.
Oh, excellent. Next question. Can you see my screen?
Just a minute, hold on.
All right. Thanks.
Okay. You there?
Yep. Can
Okay.
you see my screen?
Yep, you can go ahead.
That was a yes.
Yep.
All right. Great. Well, sorry about all the technical delays. I had hoped to be there in person, but all the passes were closed, and we had a bunch of snow here, or ice here, and snow between here and there, and so unfortunately it didn't work out. But I'm pleased to be able to present tonight to you guys at this forum. I'm going to talk a little bit different topic than the previous presenters. I'm going to be talking about nanostructures in manufacturing, but instead of nanoreplicators, if you want to talk about sort of a Star Trek reference, this is more like the cloaking device. We're not actually anywhere near the point of actual cloaking devices, but in terms of spectral selectivity and controlling the radiation that gets into a building in terms of visible light and infrared light, that is something that we can have control over. So the title of my talk is talking about metamaterials at scale. So how do we make these nanostructures over very large areas, and what can they do, and where might they potentially be used in the future? So metamaterials have been experiencing a lot of interest recently in the scientific community. You'll see a lot of Nature, Science, AC Photonics, other papers. Actually, this last one at the end is for a proposed cloaking device. So besides cloaking stuff, metamaterial is really just a sub-wavelength structure. So it's a structure that's smaller than the wavelength of light that you're interested in interacting with. So that can be sub-millimeter for microwave radiation, and can be sub-nanometer, can be hundreds of nanometers or tens of nanometers for visible light through infrared. So depending on the size of the structure, you can control what wavelengths or what band of wavelengths that interact. So the reason why metamaterials are of such interest is because you can control the properties in ways that you couldn't do before with conventional materials. There's two different types essentially. There's photonic bandgap materials and plasmonics. I'll talk primarily about plasmonics in this talk here. But again, it gives you spectral selectivity, and a way to tailor the spectral selectivity allows you to get around things like Snell's law and be able to design structures that don't obey the classical optics design. So because of that, and there's actually probably a lot of different applications for these types of structures. more in the near term and also in the more long term. So I mean, they're in the microwave regime. Kymeta is making these microwave antennas that are metamaterial driven for having broadband internet access anywhere, like on planes or ships or anything like that. At PNL, we've been doing a lot of work with nanoplasmonic windows for controlling spectral selectivity of a window film on building scale. At Harvard, they've been doing some work with creating flat lenses that have the same objective power as a microscope objective, resolving power as a microscope objective. You can use them to enhance solar cells. You can use them in other applications in buildings to do something called daytime radiative cooling. By controlling the spectral selectivity of the surface, you can vastly increase the energy efficiency of that building by letting it cool during the daytime. They can be photonic band gaps in high brightness LEDs. You can control the color of things, for example, in your smartphone or in architectural windows. You can control the color rather than having to use a particular additive that may be potentially toxic. You could use just structural nanomaterials to be able to control the color. At PNL, we've also been looking at things like tamper indicating seals and dosimetry. So we can use these as of course, as sensors. And then the one that a lot of people talk about and is well known for materials is the use for cloaking. That's something that we don't really work with at all, and I think it's probably pretty far down the road for maybe a single wavelength cloaking. But that is one application that's talked about a lot for these type of materials. So metamaterials, or at least plasmonics, are the type of materials that we study at our lab, and they've actually been around for a really long time, although people didn't know it. So I think one of the first examples is people have found this, I think it's called Lycurgus cup, if I'm pronouncing it correctly, from about 4th century Rome. This actually has these little silver nanocrystals in the glass, and it exhibits this great dichroism, so it makes a nice optical effect. When you shine light on it from the outside, it looks green, and when you shine light on it from the inside, you get this really nice, vibrant red color. And so, we can use these type of materials to control the spectral selectivity of, how they manipulate the light. The nanoplasmonics are actually resonant structures, and you can think of them in some of an analogous way to an LC circuit. So you have, a isolated metallic structure that you excite with electromagnetic radiation, so visible light, or in the case of a larger one with microwave radiation. And because it is a unique isolated structure, it has associated with an inductance and a capacitance. So because you have an inductance and capacitance, you have an LC circuit which has associated with it a resonance. And so by controlling the size of these structures, you can control where that resonance occurs. And so this figure, I don't know if you can see my mouse or not, shows 3 different sizes that we've been able to fabricate, and you can see that the resonance shifts to the red as you increase the size of the structure. So the key takeaway message for the nanoplasmonics is that they're a resonant structure, and that gives you spectral selectivity in terms of the reflection or the absorption or the transmission of the material. Nanoshells aren't the only nanoplasmonic structures. There's actually a huge variety. I mean, realistically speaking, it's whenever you get an isolated metallic structure or array of metallic structures. So we can make metal cups or shells. You can make the complement structure, which would be a nano mesh or lattice. In all of these pictures, the gold material is representing a metal, and the red material is representing a dielectric. You can make these triangular bow tie effects. All of these top list of structures are relatively easily made by self-assembly hybrid template processes. The second row showing the ring, open ring, and split ring resonators, those are all structures that you'd find normally in a microwave metamaterial structure. And of course, you can make some of these by synthesis. You can either make nanorods or nanospheres that can be used for plasmonic purposes as well. So there's a very large variety of these different types of structures. So, your complexity isn't exactly just limited by your fabrication techniques. In order to make something on the size of a window, manufacturing is extremely challenging. And it's not just the challenge of being able to make these, but you also have to make them in a cost-effective way, especially for something like a window technology where the cost margins really aren't that high in terms of what the market will accept. So you're talking on the order of a few dollars per square foot. And so you have to be able to bridge that gap between something like Space Needle, which is like 200 meters in height, down to coating it with structures on the order of the size of bacteria or viruses. So all of these, you have to make an array of structures that are about, each individual component is about 100 nanometers in diameter. So the challenge is to be able to span those 9 orders of magnitude in terms of a manufacturing. So there's obviously some challenges and limitations there. So I'll sort of give hopefully an overview of different fabrication routes and sort of what works and what doesn't work. So in terms of nanofabrication, there's generally two routes. There's top-down and bottom-up. So top-down, it would be things like E-beam, ion beam, or I think this other method is called nanoscribe. And the top images, you can make pretty much whatever you want. As complex a structure as you can imagine. So for example, people have been able to make these little nano Eiffel Towers. So there's a lot of complexity that you can do, but because it's a serial process, it's incredibly slow compared to manufacturing processes, and also it's typically not scalable to doing much over some wafers. So to make large-scale structures is pretty much impossible. So, let's go by Feynman as, there's always room at the bottom. Well, there's a bunch of other approaches that you can use, sort of this bottom-up approach, to be able to make these nanoplasmonic structures over large areas. The simplest would be to synthesize, the solid nano, particles or nanorods, and then one can disperse those in, say, a paint or like that. But that doesn't really give a lot of flexibility in terms of the response. So we take sort of a middle ground, looking at self-assembly processes, taking essentially a disordered structure and creating a patterned structure out of that by the intermolecular forces between the different particles and the capillary forces and things like that. And so we can make these self-assembled structures and use those as templates, or potentially just use the self-assembled structure as it is for the nanoplasmonic structures. Because these use wet deposition, they're usually very fast and they are scalable to large areas, and they also mesh with manufacturing techniques that are already out there for other things. The limitation or the drawback is that the structures that you make through these methods are typically very simplistic. And so I'm hopefully going to give you some examples of the structures you can make and maybe some ideas of how to make them more complex for improved functionality. I'd be remiss if I didn't mention sort of a middle ground, and that's nanoimprint lithography. So nanoimprint is where you take a hard master or mold created typically by E-beam or photolithography, and you can make the whatever nanostructure you want. That's going to be very expensive, but then you can replicate that in a soft material like a polymer over very large areas in a roll-to-roll process. So this potentially allows you to sort of strike a middle ground between complexity and cost and scale-up. These devices are still kind of early in terms of market adoption. I'm not sure that it's something that would be widely adopted for something like, say, a Windows technology. At least I don't, based on conversations I've had so far, that's probably not the case. So things like wet deposition only would be more amenable to that. So we've made a number of nanostructures in our lab. We've made the nanoshells, nanomeshes. We've also done some imprint lithography to make a nanocylinder. The nanocylinders are a very interesting animal because it actually is nanoscale only in one dimension. So if you take a cross section perpendicular to the lines, in all of these, the bright regions are metal and the dark regions are dielectric. So this, I don't know if you can see the mouse or not, the bright region is the metal and the dark region is dielectric. So when you look across the line, you get this sort of nanoplasmonic resonant response. But when you look along the direction of the line, you are essentially seeing an infinite metal surface. And so you get a very strong polarization dependence. So go a little bit into some of the details of how these different structures are made and how they respond. The first one we've looked at quite extensively is the metallic nanoshell, something developed by the Hollis Group at Rice University a number of years ago. We've taken what they've done and figured out ways to make this into a dense mesh that can be scaled over large areas. In terms of what we've been able to demonstrate so far, in working with an industrial collaborator, the collaborator has been able to generate hundreds of square feet of nanoparticle template, and I'll show a photograph of that in a few slides. So it is something that really is scalable to large areas. So that's why we've been looking at, for say, things like Windows technology, because you have to have something that you can scale at relatively low cost. So the nanoshell is actually the sort of open ring resonator analogous structure for microwave metamaterials. So this is the 3D nanoshell, and this is the 2D open ring resonator structure that you'd see in microwave metamaterials. So as you increase the size of the structure, as I showed before, you get a change in the resonance. So you can tailor that to anything between some of the UV all the way to the near infrared. And typically, because we're interested in window films, we've been looking at near infrared responses. So we're looking at structures on the order of 100 to 300 nanometers in diameter. So how are these made? They're made by a hybrid process. So first off, start out with wet deposition of the monolayer of polymer nanoparticles. So we deposit the polymeric nanoparticles over, again, we can deposit them over, well, the industrial partner can deposit them over hundreds of square feet in a sort of a roll-to-roll method. And then we do a plasma etch of the nanoparticle nanoparticle monolayer. So this is the starting point, the upper figure, and then we etch them. We can see the insert of the lower figure, and then we deposit a metal on it with directional metal deposition in the vacuum process, and then that's what this lower figure shows. These are all the nanoshells. And the reason why we do the plasma etch is because if we didn't etch them, when we deposited the metal, we would get a rough surface, rough metal surface, and that doesn't have the plasmonic properties. So to create the discrete shells, but also keep them as densely packed as we need, we have to do a plasma etch for that. These can be made on flexible surfaces. You can either directly deposit them on flexible surfaces, or you can remove them by putting down an elastomer and peeling them off. So you can create something that's very flexible. So there's potentially some room in the future for these things to be incorporated into wearables because the nanoshells are independent, so they you don't have an issue of cracking or breaking of the films. So that might be wearables might be something where these things could be very useful. In addition to the nanoshell structure, we essentially get for free a secondary structure, which is a nanomesh. You can see the SEM here. So what happens is when we deposit the metal on top of the shells, we create the nanoshell, but we also get a shadow pattern on the substrate. And so when you peel off the shells embedded in an elastomer, then what you're left with is a series of holes in the metal. And so again, the bright region is the metal, and the dark holes are the dark regions are the holes in the metal. And so you can change the size of the holes and the spacing, and that will dictate the resonant properties of this pattern. And you can take that a step further by controlling the the etching of the material, you can create these bow tie type structures, and you can vary that essentially continuously between the bow tie type structures and the lattice structure. So you can make, essentially with one deposition technique, you can make at least 3 different types of different plasmonic structures. And so these all should be very well adaptable to large scale and coating of things like windows. This just shows that we can do some prototypes in the lab. What I wanted to show is that this here is actually a 100-foot roll made by our industrial collaborator at PPG Industries of the nano template material, and the bottom figure actually shows a section of that material, showing it's got really good uniformity. So this is something that, using a roll-to-roll technique, one could actually make very large areas of these films. So that's why wet deposition is a very interesting technique, a very good technique for these type of nanofilms. We have also done some fabrication with nano-imprint lithography, where we emboss a grating into a structure and then coat with metal from one angle to create these nanocylinders, which I talked about earlier. So nano-imprint does, again, hold a key to making a lot of different, more complex structures. The other thing that we're always looking at is, are there ways to make the structures cheaper? Because again, in order to increase the marketing potential for these structures, one has to lower costs as much as possible. And so we start thinking, is there any way we can go simply to just wet deposition techniques to make these structures, rather than having to go from a wet deposition route to a vacuum deposition route to put on the metal. So what we can do is to make everything with wet deposition by using sinterable metallic nanoparticles. So we start off with, again, with a template monolayer, this time of silica particles, so they're thermally robust. And then we come in with a much smaller silver nanoparticle, and we essentially, by wet deposition and controlling the wetting and the capillary forces on the surface, we can then controllably place the metal nanoparticles into the interstitial regions of the larger spheres, and that's shown here. And then when you sinter the material all together, you end up with the silver particles sintering together, and you form this metallic mesh. So again, the bright regions are the silver, and the dark regions are the silica spheres that are sticking out of the surface. So in that way, just using wet deposition, you can create structures that are nanoplasmonic. And so, this is something that is still in the really early stages, and so the film quality isn't that good. But again, you don't have to resort to using a vacuum for this. So this is potentially a lot less expensive than the other techniques, and in large area applications that may be key. We don't have to do everything in the laboratory. We do a lot of design work, so you can actually determine what the response of these nanoplasmonic structures are going to be, so that you can kind of design things and figure out where, what structures you need to build. So we can use finite time difference domain modeling. We can figure out what the near field response is in terms of where is the resonance occurring. That's critical for things like window applications, to know whether the response is in the visible, which typically you don't want, although you could use it for color tinting purposes. But you typically want to have the response be in the near infrared. And so we want to be able to control that so that we get the right spectral properties of the window. So we can do that using numerical modeling to save a lot of research dollars. So we can also use that to come up with sort of rules of thumb in terms of what happens when you change different parameters in terms of the fabrication, in terms of increasing the thickness of the shell, or decreasing the size, or increasing the duty cycle. So we can develop sort of these phase-based mapping or rules of thumb. So we kind of can figure out generally, if we were to go design a particular structure for a particular application, what our needs are, then we can sort of figure out, okay, well, generally we need to change this or change that, and so that's a really useful tool. For example, we can look at a structure that we were building for IR blocking in Windows. We needed to block out the IR, so we needed to look at a combination of 3 different nanoshell structures, and we need to know what the combination of those structures look like in terms of the infrared reflection. And so we could use numerical modeling to combine them and figure out what that effect would be. So I can talk now about some of the optical response of some of these films. So you've hopefully given some motivation as why we're studying them. Talked about some of the fabrication challenges, and then what we can do in terms of modeling. So what are some of the optical responses? So this is this first slide here talks about the nano cylinders that we're making. So again, these are actually gold. We're using gold as a surrogate material. Typically, Windows films you'd want to use silver or aluminum. And so we make these simple line space gratings. These were made with imprint lithography, and then we coated them from 45 degrees with the gold to make these nano cylinders. And these structures show a dichroic response. The transmitted light is mostly blue, and the reflected light is red. And if you look at the resonance, you can see that it occurs at about 700 nanometers. So the interesting thing about these, as I mentioned before, is the fact that they are highly anisotropic. So if you look at the polarization response in terms of this structure being rotated about the axis either parallel or perpendicular to the lines with the polarization either, again, perpendicular or parallel to the line grating, you can get very different responses. So I'm not sure if you can see the mouse, but in the bottom, so actually in both cases where you see the dark blue bands, those are the cases where the polarization is perpendicular to the lines. And so there you're getting a strong nanoplasmonic response. The reason why the lower left one is highly angular dependent, the x-axis is the angle of incidence as we rotate the sample about the normal incidence beam. The reason why that's angular dependent in the lower left is because you are changing the cross-sectional projection of the electric field on the shells. And in the upper right figure, there you've got the polarization still perpendicular to the lines, but now the projection isn't changing because of the way you're rotating the film. And in the cases where you don't have perpendicular crossing of the polarization and the shells, and the lines, then you get something that's not plasmonic, and you don't get a resonance at all. So these are really interesting structures. They might be potentially useful in bringing daylight further into a building space, or reducing glare in your windshield or on your smartphone screen, or potentially in some advanced tags and seals. So these are some pretty interesting optical responses you can get from a very simple structure. So one of the things we did a lot of was to look at how can we use these types of structures for increasing energy efficiency in buildings by using these in window coatings. And so if you can control separately the visible response of a window coating and the infrared response of window coating, then you can keep the infrared light, keep the visible light, but block the infrared and potentially block the infrared in a dynamic way. There are current technologies out there for controlling solar heat gain in a building, but typically those, so like electrochromic and thermochromic, will turn dark when they're blocking. So you lose the view and you lose that beneficial daylighting. So we were looking at spectrally selective ways of doing that. So these are something that would have to be scalable to very large areas to be able to be applicable to things like a skyscraper or to even to an automobile window. So we can use these nanoshells to do this. Here's an example of 3 different nanoshells combined together and the effect on the solar spectrum. So we can see we can effectively notch out the near-infrared signal to mitigate that solar heat gain using those structures. So this is something that would behave like a low-E window but would use significantly less metal and would also be amenable to things like daytime radiative cooling because it doesn't block into the deep infrared if you don't need it to. The other thing that these spectrally systems can do, as I mentioned, is to allow for dynamics. So because the optical response of these is dependent entirely on the geometry and the orientation of the nanoshells, when you disorient the film or essentially randomly orientate the particles, then the projection of the incident light, electric field on the particles reduces, and instead of getting infrared reflecting, you get essentially infrared transmission. So we incorporate essentially a buckling transition or a wrinkling into the film where in the cold state, the film is wrinkled and the shells are all misoriented and infrared light comes in. So you get that beneficial heating from the solar heating into your room to warm it up. But when the window film heats up and so the room is hot, you no longer want that solar heating. The film has now expanded and is now flat, and so you get this really good, well-oriented film that can then reject the infrared light, and so it can switch reversibly based on the temperature of the window between a buckled film that's allowing infrared light in and the flat film in the hot state that's blocking the light. And this is an example of one of the films that we made, so it's got pretty good optical transmission as well. So there's some really interesting things you can do with incorporating dynamics into some of these nanoplasmonic films that are especially selective. Other things that we've been able to do with these structures is to look at using them for sensing. What we were primarily interested in was using them for radiation sensing. So because the nanoshell is essentially a cavity or a resonance cavity, if you change the properties of the material inside the shell or actually right next to the shell, if you say, for example, have an overlayer of material that's sensitive to radiation, if you damage that material and change its index of refraction, then you can get a shift in that resonance. Essentially, it's like changing the capacitance of a cell, and then you're seeing a shift in the resonance of the LC circuit because you've shifted that capacitance value. So we were able to look at films that are created with acrylic, essentially very thin acrylic films. You don't see much of a shift in just a thin acrylic film. I mean, there is a slight shift there, but you can't see it because it's so slight. But when you incorporate the nanoshells into the film and do the same exact experiment, you get a very dramatic shift in terms of the interference fringes from the film because of the essentially the resonant enhancement of the nanoshells. So this can be used as an optical dosimetry, and that's very important because you're basically looking here only at the reflection of the film. So in the case like Fukushima, you really don't necessarily want to be right up next to the source or the place where you're trying to see how radioactive it is. You can then look at this from a standoff method to in case where the fluence is quite high. We've also used these to make tampering and tags and seals, so we can actually make these transparent. So these can be put over video monitoring things, or in the case where you need to have high transparency still. This is a prototype, so the transmission quality isn't that great, but I mean it's like about 70-something%. The optical quality would be better if we had more time to perfect it. And so because these have a very unique spectral signature, it's very hard to damage them and still retain those properties without noticing it. Additionally, we could incorporate, by incorporating silver, we can get an effect where the plasmon resonance essentially turns off because the silver oxidizes. And you can see in this bottom figure, you go from a clear state to a dark brown state when the silver becomes oxidized in these nanoplasmonic films. So the main thing in this slide here is this is a nanoplasmonic film. It's encapsulated in an elastomer. And this center region where you can see this very vaguely or barely you can see this circle, this central circle was cut and then rotated slightly And so by eye, you can only barely tell that it was changed. But then when you look at multispectral analysis or hyperspectral analysis, you can see that that center structure was definitely tampered with, and also there's a sort of a damage region around it. And so it's designed to not show up in the visible, but to show up in the infrared, and that makes it actually a lot more difficult for someone who's tampering to be able to correct for what they've done. So it's essentially an added security feature. So we can also make spectral barcodes out of these by incorporating the addition of multiple resonances. This is incorporate 1, 2, and 3 resonances. This is the combined structure. So for unique authentication or essentially a spectral barcode of things. I think I will skip the summary here, and I want to talk just for a minute or two about some of the things you can potentially do using imprint lithography. So, I've talked about nanoplasmonic structures up to this point using just self-assembly processes, but, I think that long-term nanoimprint lithography could play an important role, but you're still probably going to want to be able to make as much complexity as you can sort of post-processing rather than necessarily having to incorporate a very complex structure initially. And so the way you can do that is by looking at the thermal instability of the polymers. This is work that was done at NIST back when I was there about 8 years ago. So there, we figure out essentially nanoscale structures are pretty much unstable because they have all this surface energy that wants to make them flat. So you can see all of these little sharp corners want to go away, and the surface wants to essentially height decay into a flat substrate. And that's exactly what will happen if you let it go. When you take a polymeric surface and you heat it near the glass transition point where it can flow, it'll go flat. What's more interesting, other than this sort of slumping behavior, is if you look at threads. So if you take a liquid thread and you, that's traveling along, it will break up into droplets. So, there have been examples in literature where they'll take a series of polymeric threads that are isolated on the surface, and you can break that up into droplets. So that's a way of doing some patterning. One of the things that we did at NIST was to look at, okay, let's add one more level of complexity. What if we include a residual layer between the polymer threads, which is actually very easy to do, and it's actually easier to do than having no residual layer. So what happens there actually, in some cases, is you get essentially a collective instability. So you'll get lines forming what looks like a sort of a zigzag pattern, or they're all undulating. And so this is actually just another flavor of the Rayleigh plateau instability, where the surface is just trying to decrease its surface area, and so you get this varicose mode and sort of the inverse of the varicose mode, which is the zigzag instability. And so you can use that to pattern the structure, and you can potentially make things that are more complex that can be useful for nanoplasmonics. And you could further enhance that using chemical patterning. If you add let's say a fluorosurfactant to that material, and then let that surface decay, you can create chemical patterning. So you could do the same thing potentially with metallic nanoparticles. And so this is just another way of using sort of de-wetting or thermal instabilities to create more complex patterns from simple structures. So I think I'm just out of time, so I want to wrap it up saying, these materials, a lot of people think of these as cloaking structures, but what we're really focused on is using them for spectral selectivity to be able to control and manipulate light at the nanoscale. But we've got to be able to do it over, bridge that 9 order of magnitude gap to be able to create something that's amenable for building a vehicle or even your cell phone screen. So, that's a really serious manufacturing challenge. Cost is definitely a deciding factor in a lot of these, but I think there's a lot of room for potential application there. And I'd like to finish off by saying thank you to everybody at PNL and NIST who contribute to this, and thank you all there for your time and letting me go last. So, thank you.
I guess with the floor is open, any discussions, and we can start off if you want to join us at the microphone.
So other than the making materials from organic sources, I'm mostly interested in fibers and making new clothing materials. What do either of you see in this field for that type of technology?
Well, I mean, in terms of polymers and fibers for new clothing materials, I think that's something that's going to be directly accessed by some of the synthetic biology techniques that I talked about earlier. And so, things like better nylon, softer silk, all these things. These are properties that eventually, depending upon your precursor, right, that you're using to actually make these polymers, that's going to dictate the actual properties of those materials. And so by generating kind of a variety of different kinds of precursors, and then having the microorganisms make them at scale, you'll be able to, I think, access these types of interesting polymers and fibers. We kind of already saw that a little bit with our collaboration with Invista, where they were interested in producing the precursors for nylon from a bio-derived source. And so you're going to see a lot of that, I think, in the next 10 or 15 years. So.
In our field, we're seeing a lot more organic semiconductor work being integrated into fabric itself. A couple weeks ago at the CES, there was a demonstration of some energy harvesting fabric where they're taking and leveraging organic polymers that are semiconducting polymers in order to store energy from just displacement and diffusion of ions through a membrane. So.
I'm loud enough, I don't need a microphone. I was wondering if much work has been done on corrosion protection of metals. It may sound really mundane, but it's kind of cost society a lot of money. Has there been any work on that? That's the first question. The second one is, you showed a graph with multiple pathways, and you showed blue dots where nature doesn't have those things. You can prototype those things on a computer and then manufacture something. So how do you mitigate the potential risk, or what are the risks? Is somebody really looking at unintended consequences of the technology?
Okay, so I'll answer your first question. I'll get your second one, which is kind of the gray goo hypothesis. As far as looking at anti-corrosives, anti-fouling things, yes. So people are interested in these kinds of things because they've found various organisms can create essentially what are similar to anti-fouling compounds. And so if you coat the inside layers of pipes and things with these kinds of compounds, potentially biofilms, you will have an anti-corrosive layer. And so yes, this is something of interest to folks at this point. And people are looking at it. And in terms of your second question, which is the ethical, sort of moral consequences of this technology, it's a tricky question. I think it's something that so first of all, I think it's something that we scientists kind of have to think long and hard about. In this, as far as the synthetic biology community is concerned, and I know there have already been several attempts up front to basically organize and sort of build consensus around some of the ethical and moral issues beforehand, as opposed to, for example, post, with some of the other, nuclear bomb type technologies and things like that. That thinking came kind of afterwards. I'm not sure I'm able to answer your question directly, I feel like. But yes, there does need to be some, it could be a combination of self-regulation and government regulation in terms of, someone is not going to engineer some sort of, I don't know, biowarfare, right? For example, type of thing. Yeah, that's kind of what you're getting at. Yeah.
Whether knowingly or unknowingly.
Right. Yeah. I mean, so there are some kind of sort of movements in the industry to protect against some of those things, and government definitely, I know, is looking at this type of thing. So, for example, when you order DNA, right, the DNA synthesis company will run a check to see essentially what you're ordering, and so if it comes back that you're ordering something, for example, from a pathogen, they will flag that and they will ask, why are you doing this? And you have to give them a good reason. And if you don't, well, then they'll reject the request. So these things are starting to sort of fall into place, but I think it's still somewhat early stages for the synthetic biology community, and so we're all working this out as it goes along. But I'm fairly confident that some mechanisms will be put into place such that this kind of thing, the probability of this type of event happening is very small. So. Yeah.
So this isn't directly about what you've been talking about, but it seems like it's related. Can you talk about work that's being done to use not just organic molecules, but organisms to do some of this work? So you're talking about your biology, you're using the cell pathways, but it sounds like you're doing it mainly by mimicking the pathways, not so much changing an organism to do the work for you. And similarly it seems like it could be possible in semiconductor fabrication, not just using the lattice of an organic molecule to do something, but actually to use the organisms themselves. So if you could talk about that, that would be interesting.
Right. So this is definitely something that people have been looking at. I think primarily, if you want to compartmentalize it into a field, it's kind of the bioengineering field, right? To do kind of neat tricks with organisms, and Michael actually had an example of this on one of his slides, right, where they have the bacteria, right, where they were kind of spinning that wheel. So there's been a lot of sort of fun, initial kind of, I guess, forays into doing that kinds of things. Not necessarily always using bacteria, but sometimes using viruses, for example, to pattern nanowires and things like that. Yeah, I'm trying to rack my brain here. I'm not an expert in that area of things. The synthetic biology field is very large. Yeah, I guess what I can say is yes, people are looking at this. I unfortunately can't pull any examples out of my head at the moment of this. Maybe Michael knows more.
So definitely we've seen integrating both as an analyte. So some of the enzymes or biomolecules that are used to biofunctionalize have certain binding sites, and they will change resonance as a certain analyte will bind with them. So we've seen biological detectors generated using these kinds of either virus or bacterial devices as the interstitial, that biointerface between the electronic sensor that's just measuring a change in resonance, whether it's optically or electrically, and the interface at the biological molecule that it's looking for, right? So it's got a certain receptor that it's looking to match with and key with, and based on where you see that change or shift in resonance, you can isolate what has triggered. We've also seen biofunctionalizing the end of certain bacterium to carry inorganic molecules, usually like gold particles or some kind of single atom type molecule, and then that'll form a surface on the end. So there is some self-assembly, that bottom-up type of manufacturing using biological sources, but it's kind of tailored.
Yeah, so I just thought of one example that I now recall after Michael's text there. So basically, this is not for bacteria or viruses or at the nano level, but it's still kind of detection of molecules at the nano level, which is unfortunately, I can't remember her name, but essentially, one professor has engineered essentially an explosive sensor into plants. And so the plant leaf has been engineered with a novel biosensor, such that when the explosive molecule binds the sensor, there's a downstream signaling cascade, such that the plant's leaves will, for example, turn a color. Right, so turn from green to white, and so you can imagine that DARPA, for example, is very interested in this kind of thing for defense purposes. But along those lines, yes, there's a lot of interesting sensing work going on. So maybe even, for example, in cleanup of heavy metal spills, oil spills, things like that. So.
Michael, so when you talked about the DARPA CHIPS program and integrating these chiplets into separate components of the processor, like AC or ALU, memory chips, stuff like that, could that be a way to continue Moore's Law level computing advances without having to continually increase transistor concentration?
I mean, I don't think, so Moore's Law is talking about transistor density, so it's really a 2D problem. So I don't think you're going to see 2D advancements, farther, too much further down. I mean, we're starting to approach dozens of atoms. So I don't think, at some point that's going to peter out, but if you look at it volumetrically, sure. And the fact that you're looking at chips as taking these IP blocks, you can do massively parallel functions, and 2.5D is definitely a method that's a single stratus, and then you can imagine stacking those different strata, you're going to get lots of functionality. So, if they employ these thinning techniques and profile reduction, you can stack those up so it'll look a lot more like that memory stack basically at the end, but with all those 10 nanometer chiplets kind of populating a cube.
Andrew, you talked about like man-made space and biospace, right, and then theoretical biospace. How do you look at an enzyme reaction or set of reactions or set of biochemistries in some large database and ask, what is the adjacent possible for some set of biochemistry given known enzymes?
What is the enzyme? Okay, so I see what you're asking. Basically, we do this in a way that we turn the generalized enzyme reaction operator, essentially. And so the way you do this is you have a set of known enzyme chemistries, and then you break it down into the subsets of the reaction that you know are similar, right? So the actual bond breaking and making events. And then everything else is essentially, if you remember your organic chemistry, kind of an R group. Right, and so this is it's not always just the chemical bond, right? It could be additional adjacent information, like maybe you need a ketone off the end to drive that particular reaction to go, or having some sort of activation group or functional group off the end to drive that reaction to go. But you basically take the generalization of the known enzyme reactions, and then with this sort of operator, like this is how the reaction is supposed to go, you're able to apply this to the compounds that you're interested in over and over again to see what kind of transformations you're going to get. Does that approximately answer your question? Yeah. Okay.
For the last presentation, I noticed that the National Security Agency was listed as a funder. Why would they be involved in that? It was NSA.
NSA was probably interested mainly in the anti-tamper technologies that they were working on. So part of their mission is information assurance, and so they worry about things like, do bad guys do tampering in those specialized systems? So that's where that tag development probably got funded from.
one last question before we close. Our season theme for all of our programs this year is Transforming Tomorrow. And so with the technologies that you have talked about, and we've looked a little bit into the future, what is the biggest transformation that you see happening with your technologies, with your molecular manufacturing in the next 5-10 years?
Future is really hard to predict. I think the primary things we're going to see, at least in our immediate field in synthetic biology at the industrial level, again is kind of going. The impacts are going to be at the industrial level, right? And so you're probably not going to see everyone in their home has a mini bioreactor. That's not going to happen for a very long time. But you're going to see a cleanup, in a sense, of the chemical industry. So many chemical companies are going towards bio-derived products and sort of revamping their line. So from a sustainability standpoint, I think our processes from the chemical industry are going to become much more sustainable, right, in the next 10 years. So from a planetary health impact, I think that's going to be a very good thing. Sort of in terms of new things, you're probably going to see some very interesting new bio-derived things, which potentially then are either higher performance, cheaper, maybe biodegradable. So kind of some of the things I alluded to probably on my last slide of my talk. But yeah, I think most of the things will come at the industrial end and not at the sort of the consumer end.
So I think, mobile computing and all that is kind of saturating. And, I think there'll be a continued focus on energy, removing the need to do constant charging or nightly charging. So I think continual charging, energy harvesting will continue to grow. Wireless transmission of power from just harvesting ambient RF, since it's fairly ubiquitous at this point. I think those trends will continue to grow, and as power consumption decreases. So I'd like to see, or I'm hoping that we'll start seeing less of a dependence on lithium-based batteries. I'm sure Samsung would agree with me after the recent debacle. And then I also see, the smart implants, ways to monitor human health almost continuously or holistically. The biggest challenge being not necessarily actually creating those devices, or it's really the FDA hurdle that seems to be blocking, because it's trying to get VC funding in a biomedical implant is really hard to do if you haven't gotten FDA approval, and it's really hard to get FDA approval if you don't have a lot of money. So I see logistics probably being the biggest hurdle in that arena.
Great. Well, thank you very much for your time today. And just a reminder, our next programs are Connected Cities and 3D bioprinting. So I look forward to seeing you at one of those programs. Thank you.